Okay, let's talk encryption. Encryption is essentially the process of converting plain text, clear text, two different words for the same thing, to some form of ciphertext, which is the encrypted version of the same text. One way is to do simple substitution. Another way is a much stronger encryption. In the example here on the screen, we have the blowfish cipher using the key of my name. And this is a test message. We get the DR8MX blah, 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 that gobbledygook, which is our encrypted text. And on the output then, if we re-enter the key and we enter the gobbledygook, we get the message back out. And that is an example of symmetric encryption. Symmetric encryption uses the same key to encrypt a message that it uses to decrypt a message. And this is, when you think of a decoder ring or one of those puzzles with the famous quotes that you might do in a newspaper, if you still get the newspaper. I don't remember what those things are called. The puzzles, not the newspaper. I remember what a newspaper's called. With the symmetric key, to encrypt and decrypt a message, you need to have the key. And ideally, in a good cipher, your key would be a lot longer than just the example that I used, my name. You would have a significantly longer key, and that would be hard to guess, because otherwise it's going to be just a simple matter of decrypting it, of guessing what the key is and decrypting the message. So you're going to want a super long key. And in order to encrypt and decrypt messages, you need to share that key with everybody who needs to have access to those messages, which is not always the easiest thing to do. You need to pass that around. Some examples, a Caesar cipher, ROT13, those are examples of simple substitution ciphers. Decoder rings, like I already said, Drinkmore Ovaltine is an example of a symmetric encryption algorithm. Once you have the cipher, then or the key, that you can decrypt a message. There's also more complicated ones that we'll briefly talk about. The book talks about those a little bit more. So ROT13 or ROT13 is probably the simplest of simple substitution encryption. I use that term loosely because in the case of ROT13, you're not actually getting much data security out of encrypting your data in this way. It's very trivial to try it out and see if it works to turn your gobbledygook back into a message. So essentially you're rotating each character 13 characters forward in the alphabet. So A turns to N turns to A, B turns to O turns to B, etc. Those are the nice thing is that it's very easy to use, and it's very easy to encrypt and decrypt a message with this. Again, you're not getting much data security out of it because if you look at a message and if you've looked at enough messages, it's pretty easy to recognize a ROT13 or to try out and see if ROT13 decrypts a message. There's much better options like the Advanced Encryption Standard AES, which is currently the industry standard for symmetric encryption. So this is what's called a block cipher. And again, we're not going into details here, but it does more than the simple substitution where you take one letter and turn it into another letter. It does a lot more, and it processes essentially the whole message altogether rather than one character at a time. And that provides increased security because one character at a time, it becomes easy to recognize patterns, which is why that's what the puzzles are that you do in the newspaper with the famous quotes. Because simple substitution ciphers are relatively simple to figure out using patterns like most common characters and things. A block cipher removes a lot of that simplicity and makes it harder by processing that whole message at a time. So these use, remember, the length of the key is important to figure out how secure you're going to be. And currently, at least, they say until 2030, we're good with 128-bit keys. And unless something crazy happens with advances in computing power and computing speed, then 128-bit keys are going to be good to go until 2030. Then there's already standards built in, and you can use these now to use 192 or 256-bit keys, which drastically increase the time it would take to figure out what your key would be. So The weakness of symmetric encryption is that you have to share that key. And like they say, 3 people can keep a secret if 2 of them are dead. Secrets are really hard to keep, and a shared key means that if anybody gets that key who shouldn't have the key, everything is compromised all at once, immediately. And every message you've ever sent has been compromised. Every message you send from then on will be compromised. So using symmetric keys is great as long as you can keep that key a secret. But as soon as that key gets compromised, or as soon as one person who has that key gets compromised, then everybody's compromised all at once. So they've come out with significantly better options for not having to share a key, and that is called asymmetric encryption, aka public key cryptography, public key encryption. There's a lot of other words for it too. And the way this works, the way asymmetric encryption works, is by using 2 keys. Rather than using one key to encrypt and the same key to decrypt a message, we're going to use 2 different keys, one public and one private. And the beauty of this is you keep the private key and you never have to share the private key with anyone. Unlike the symmetric key where everybody has to know it, you keep that private key and never tell anyone what your private key is. But you can share the public key with the world. And the public key is what would be used to encrypt a message destined for you. So if I wanted to send you an encrypted message, I would need your public key. If you want to send me an encrypted message, then you need my public key. And then the private key, that one that you're never supposed to share, is used to decrypt that message. If you take my public key and encrypt a message for me, then only someone else with my private key, meaning should only be me, is able to decrypt that message and read it. And the same, if I use your public key to send you a message, then only someone with your private key is able to decrypt it. So just like our example on the bottom right here, so Bob uses Alice's public key to encrypt the message, turns it into some gobbledygook, and then Alice uses her private key to decrypt the message and convert it back into hello Alice. That means that nobody in between, nobody has to share that private key, and so none of the secret keys have to be shared with anybody, and that's amazing. And it facilitates all sorts of things. So again, to encrypt a message, I'm going to take the public key of the person I'm sending the message to, and I'm going to encrypt the message with that. And the beauty is that public key is, in the full meaning of the word, it's public. There is no reason to keep it a secret. You can share it with everyone. You can post it online. You can post it on your website. You can post it on Twitter. You can do whatever you want with that public key. You could post a picture of it on Instagram, and nobody's going to be able to do anything with it, except now they're able to send you encrypted messages, which is great. So they take that public key, they encrypt a message to you, and then you use the private key again, and there should only be that one copy of your private key. If you have 3 computers, you probably want a copy on each computer, but for the most part, you take one private key, and only you have access to it, and only that private key is used to decrypt messages that were encrypted using your public key. Sounds more convoluted than it is. It's really very simple. Public keys are used to encrypt, private keys to decrypt messages. So examples, OpenPGP, PGP is an example that can use asymmetric encryption, and you could send encrypted emails using asymmetric encryption. And SSL, or transport layer security, secure sockets layer, transport layer security, these are the protocols that underlie HTTPS. And those are other examples of asymmetric encryption. And that is how you don't need to talk to Google first to get their key before you can start sending encrypted traffic to Google. Google broadcasts out their public key to the world. You use that public key to encrypt a message for them. The underlying math behind it, we won't go into a lot of depth here. If you're interested, Google and Wikipedia have a whole bunch of information. A whole bunch of other websites have a bunch of information. Really, it comes down to using large prime numbers. And we'll talk about it on the next slide here. But just in case you're interested, the largest known prime number at the time of this recording is 2 to the 74,207,281 minus 1. And that is a prime number with over 22 million digits. That's really, really big. We're not using prime numbers quite that large for asymmetric encryption. We're looking at 100 to 1,000 digit primes, which is still very large, but not nearly that large. Before January 2016, the last largest known prime was discovered 3 years earlier and had only 17 million digits. So we've got 5 million more digits to work with here in our large prime numbers. So the current standard is RSA-2048, uses a 2048 bit key, and using those large prime numbers as your private key. And only you know the two large prime numbers. And then you multiply those two primes, and that's your public key. And this works because using really big prime numbers, factoring those big numbers is hard. And it's hard for computers to do, and it would take a really, 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 really long time. We're talking many, many years, thousands of years, millions of years, for a computer to be able to take the result of multiplying those two large primes and factor that out to what would be your private key, which is those two large primes, the actual numbers that go into that. So factoring big numbers is hard, so that's how all of that works. And again, this is not nearly as large as the largest known primes with 22 million digits. We're talking 600 digits here for RSA-2048. It's still a really big number. If you thought IPv6 was a big number, look at that number, even bigger. So another option that's coming around now that's kind of replacing the RSA encryption is elliptic curve cryptography. And if you look at security certificates, if you're in the habit of glancing at security certificates as you browse the web, you might see more and more of this. And we won't get into how this works either, really in any depth. But what you can know is that it provides the same security as RSA with much shorter keys, in about 256-bit keys compared to the 2048-bit keys of RSA. So significantly shorter keys with the same level of security, which is awesome. The key with public key cryptography, and the reason that the keys have to be so much longer, remember AES, 128-bit key is plenty for the foreseeable future, really, versus these 2048, which is significantly longer for public key cryptography. And the reason the public key keys have to be so much longer is because you're sharing half the key, that public part of the key, with the world. And if it was a smaller key, then it would be easier for them to do the math to figure out what your private key is. So we have to make that bigger to make it harder to figure out what the private key is, to the point where it's mathematically and computationally and time-wise, it's infeasible to even try. So again, SSL and TLS, those are used to encrypt the web. So essentially, they operate SSL. If you visit an encrypted website, you're using public key cryptography. And the way that works, again, you take the public key of whoever you're trying to send to, Google, for example, and you encrypt a message for Google. And then Google can use their private key to decrypt that message and then send you a response. Pretty awesome. So there's also PGP and GPG. PGP stands for pretty good privacy, which is a kind of a misnomer. It's actually really good privacy. So PGP is a standard to encrypt messages, and GPG, or GNU Privacy Guard, is an open source implementation of PGP. So you can use one to encrypt messages for the other, etc. So you can use that to encrypt files, you can use it to encrypt emails, and we will have an experience doing some of that in the class. So then there's SSH, and with SSH, you can encrypt messages using, or you can authenticate with a server using a private key. So, and we'll talk about that. It comes in digital signatures, and you can digitally prove that you are you, and the server can authenticate you using that message. Now, a digital signature is it's related to that public key cryptography. It's a part of it, And basically, you use your private key to sign a digital message or a file. And when you use your private key to sign a message, that's you performing some math on the message and basically verifying that you are the person who sent the message and the message has not changed. And you can use that, and on the receiving end, when I get a message, I can take the digital signature and use the public key that you've sent me, that you've broadcasted out to the world, and say, okay, was this message signed by Ryan? If I'm the one sending out the message, was this message signed by Ryan? Yes or no? And has this message been changed since the message was signed? And you can use that, especially useful for encrypted messages. You can use that to verify that I'm the one who sent it and that the message that you are reading is what I meant to send you. To basically fix any issues where some sort of man in the middle might take a message and modify it, especially if you're sending unencrypted text or through an insecure channel. You might worry that someone would intercept a message, modify it, and then send it out pretending to be me. Not an issue with me because I don't have anything important to say. But a digital signature would allow me to verify that I am the one who said what I said in that message, which is pretty cool. And we'll do that in the email lab as well. So the one issue with public key and private key is that basically there's no rules about who creates a public key or a private key or a key pair. Typically they're created together. It's a key pair. So I can create a key pair and broadcast out a public key. And I'm going to do it. I'm going to put one on Blackboard and you can read it and you can see it and you can open it if you want and see what it is. But you're going to import that and look at it and say, okay, this is Ryan's public key. The problem is anybody can create a public key for anybody. So I could create a public key. I've created one for me that says Ryan, that has my email address associated with it. But I could also create one that says Barack Obama, that has his email address, or that has my email address and his name. There's nothing in the creation process of a public key and a private key that requires me to verify who I am. So anybody could create a key pair claiming to be Barack Obama. Or anybody could create a security certificate for a website claiming to be www.google.com. There's nothing in the creation process that requires me to verify that I am who I say I am, that I am Google, or that I am Barack Obama. All I have to do is type in a little name or type in a URL and I'm good to go. So we've fixed that with certificate authorities. And basically a certificate authority's purpose is to distribute those public keys. They keep all the public keys and they can pass them out to everybody and everything's good to go. And they also verify and certify the identity of the public key. Essentially saying, this public key really did come from google.com. Or if you have it for personal certificates, email certificates, this public key really did come from Ryan Schetzler, or this public key really did come from Barack Obama. And you could verify that using a certificate authority. And really, these are based on trust. So essentially, I have to trust certificate authorities. In order to have any trust in anything, in order for the public web to work, I have to trust certificate authorities. And I have to trust that these organizations and the Komodo and Class 3 and Entrust and GlobalSign and Thought and VeriSign and Equifax, that all of these organizations are doing their due diligence when they sign a certificate, when they sign a public key. Because if they don't, then we're out of luck and we're in trouble. And we have what's called a rogue certificate authority, where they're just going to sign off on anything. And anybody could submit to a rogue certificate authority and say, hey, I'm Google. And they'll say, oh, okay. And that's a problem. So we don't want to do that. We have to trust that these organizations, and we do trust, and you trust them without even thinking about it, that these organizations are doing their due diligence, and that when Entrust or Equifax or GeoTrust or GlobalSign says that this certificate really is for google.com or this certificate really is for facebook.com, that it really is the case. And the way the process works is basically the organization creates a certificate, a key pair, public and private key. And then they send what's called a certificate signing request, which is a request that a certificate authority sign a certificate. And they send that to the certificate authority, and essentially there's some sort of process, and everybody kind of does it different, but there's some sort of process to say, I am who I say I am. I really am Google, or I really am Facebook. Now, Google's a special case because they have their own certificate authority, but if I wanted to make one for Schetzler.net, I would submit this certificate signing request to the certificate authority, and I would have to verify that I own Schetzler.net. And I could do that a variety of ways. And then basically in response, they send me that signed public key and the signed private key that says, you are who you say you are. And then I get the little green icon. So this little green icon that you probably see if you use the web, that means that that certificate was verified. And if you click on it and click view more details, and then in the other menu click view certificate, you can actually see the certificate. And you can see in the case of Wikipedia, it was signed by GlobalSign, and it was signed on, it looks like December 12th or December 10th or October 12th, I guess, depending on how they're showing their dates. And it's good through, must have been December 10th. So it's good through December 10th of 2016. And then after that, they'll have to issue another certificate. And essentially, this proves that Wikipedia, that I really am at Wikipedia. And if I go to a website where the certificate has not been signed by a trusted authority, then I get this. Essentially, this is a certificate error that says, we don't trust this certificate. They have a certificate, but we can't verify that you are actually going to InMotionHosting.com, or that the company InMotionHosting.com is who they say they are. So in this case, you might be in trouble. You might be think you're visiting InMotionHosting.com, and you're visiting something else. If they've messed with your DNS, or if they've messed with something else, then this certificate is basically wrong. And if you ever get an error like this, and you're not expecting to receive an error like this, then you got to be very, very careful before you click that Proceed Anyway button. And you better make sure that you know you're going where you think you're going. Because otherwise, if you put in a password, you might be sending that password to somebody else. You might think you're sending it to InMotionHosting.com, but you might not be. Your message is still encrypted, but you don't know exactly what the destination of that message is. So the benefits of this public key cryptography: the digital signatures provide authentication, which is amazing. Public keys make it super easy to send encrypted messages to anybody without having to share those keys. So we don't have to share any keys, and we can protect against what's called a man-in-the-middle attack. And we'll talk about that in another video. But basically, if someone in the middle is trying to receive messages and either listen in or modify those messages, then the digital signatures and the encryption allow us to protect against that and basically eliminate the need for eliminate man-in-the-middle attacks, assuming that we don't have broken implementations. So anytime there's an encryption algorithm, somebody's trying to break it. So far nobody's broken RSA or elliptic curve cryptography. So we're so far so good. But reusing keys is bad. Using keys that are too short is bad, because remember, again, you're giving half of your key out to the world. So you're giving them a clue to say, hey, this is half of my key. Good luck figuring it out. So if your keys are too short, then they can figure it out, and then they'll have your private keys, and then you're no good. Again, the other big weakness is the potential for a rogue certificate authority. Back on that slide where I showed you the list of certificate authorities, this is built into your computer, and your computer essentially says, I trust these companies. Now, there's been a couple times lately, Lenovo and Dell are the two that I know of off the top of my head, have recently added their own certificate there. And essentially their own certificate allows them to issue a secure or signed certificate for any site that they want. which allows them to listen in on anything that they want to. Or if someone compromises that private key, if it's stored on everybody's computer, then somebody could create signed certificates for any site that they want and basically get the little green icon when they should be getting the big red error message on Dell computers. So rogue certificate authorities are bad. Also, if one of these companies stops doing their due diligence, is compromised, if for some reason Deutsche Telekom decides that they're going to stop verifying identity, then I could submit a certificate signing request to them for Google and get that nice little green lock icon for google.com even when people are going to my website instead of the actual google.com. So a rogue certificate authority is really, really, really bad. But thankfully, it doesn't happen very often. All of these organizations, all of these companies have a lot of money and have a lot of interest in maintaining that status as a trusted root certificate authority. So that's it. That is public and private key and symmetric encryption in a nutshell.